All right, today we're going to do section 3.5. This is a transformation of functions. This is going to kind of expand on a little bit of what was talked about in chapter 3.3, where we talked about, well, what if you throw a negative sign in front of a function? What if you multiply it by like a half or multiply it by 3? What does that do to the function? So this is we're going to more formalize those here, but we're also going to add to that repertoire of transformations. So the three main things for transformations are a shift, reflection, and stretch. Now, shifting actually covers both the horizontal and the vertical. And then symmetry of functions and equations is this kind of like nice little thing that you get to use to make your life a little bit easier. I kind of unintentionally used it just because of familiarity with functions in the previous, not previous, 3.3 again, where I said, well, I know that if I square a number, it's always going to be positive, so it didn't matter if I did 2 squared or negative 2 squared, I still got 4. That was kind of using symmetry without flat out saying, by symmetry, I know this is true. So, first thing, horizontal shifting and translations. The key thing here, and this is what's really a little backwards to most people, just because of the way you think of a left and a right. So we tend to write it as this x minus h. And the reason we use minus h is because if you use plus, then you have to start messing with a lot of stuff and it's not as easy. So if g of x is the horizontal shift, which is where you do the operation inside of the function. So for example, let's say f of x was equal to x squared, just because that's a nice and easy function to deal with. Let's say you wanted to shift it. So let's say shift f of x, let's say 3 units to the right. And this is what I mean by it's a little backwards from what you would think. Because if you think about, here's your xy plane. There's 1, there's 2, there's 3. And there's -1, there's -2, and -3. And then I'm not going to mark these because we're dealing with horizontal right now. If I want to shift x squared 3 units to the right, so typically x squared would look something like this. So if I want to shift it 3 units to the right, then that means I need to set the vertex, to use a little bit of terminology. If I want it to sit over here and shift it 3 units to the right, so I basically have the same shape, just starts at a different point. And again, I'm no artist. There's a reason, like I said, I majored in math, not English. I also cannot draw stick figures very well, so the graphs are artist interpretations of what a parabola should look like. But if you want to shift it 3 units to the right, when you think about moving to the right, you think, oh, 1, 2, 3, positive. You move to the left, 1, 2, 3, negative. That's the correct way of thinking. But because of the way that you're shifting, this 3 units to the right is actually accomplished by subtracting 3. So g of x, which would be our shift, is going to be equal to f of x minus 3. Which is, you plug all of x minus 3 into there. So it's x minus 3 squared. The biggest mistake that I see way too many times, and I'm going to ahead and say it now to prevent anyone from making this mistake, is this. F of x minus 3 does not equal f of x and then just subtract off 3. That's a vertical shift. We're going to get to that in a second. But what a lot of people will do is they go, oh, this is x minus h, and this is x minus 3. So they go, okay, well, there's x squared, and then I subtracted 3. I'm done. No, you've done it completely incorrectly if you do this. Because you wouldn't say, let's say, I'll write it over here. Let's say you had f of 1 plus 2. Now we know that's 3, but just for example, you wouldn't say that that's equal to 1 squared plus 2. You would say it's equal to 1 plus 2, all of that squared. So whenever you see something inside of the parentheses, that means replace the entire thing. If I were to say, what is f of a smiley face, then that means you plug in the smiley face and you square it. I know it's a dumb example, but it's just kind of to reiterate. Whatever is inside, whatever's inside of those parentheses gets plugged in to x. Now it seems a little weird because you think, oh, well, I've already got x. Say it's a plus 3, say it's a minus 3, and then just replace the x. So it's not just subtract off a 3, it's x minus 3, all of that squared. Not x squared, and then subtract off a 3. But the main point I was trying to emphasize is, if you subtract the number, you shift it to the right. If you add the number, you shift it to the left. And part of that is the parabola is a really good function to think about it with. So I moved the origin, or not the origin, well, I moved it from the origin over to the right 3. So that means I went from the point 0, 0 to the point 0, 3. So what I kind of implied from here is that I needed f of 3 to be equal to 0 because I shifted it over to the right. Notice if you had done x plus 3 and squared it. Sorry, the pen was trying to run off the screen. If you had done x plus 3 and all of that squared, notice if you plug in 3, you actually get 6 squared. So you just have to be aware of what values you're plugging in and when you're using them. So just keep that in mind. And usually this is just something I would just make like a little table in your notes and just be like, horizontal shift. Add h moves to the left, minus h moves it to the right. So for example, and these I'm just going to show the graph and talk about them. Namely because it's a lot nicer to have the computer graph. These tend to have me attempt to it. So before we even do this, let's identify what the shift is. So this is x plus 2 cubed. So this is typically to find what the original function is, just drop off the plus or the minus, whichever, plus or minus the number. So the original function, this is x cubed, shifted 2 units, and you just say units. There's no, it's not like it's feet or miles or anything like that. It's just 2 units to the, and because it's plus, it's to the left. That looks like deft. Calligraphy is not a good hobby for me. And then if you look at b, so this is the absolute value of x minus 4. Drop the minus 4. This is the absolute value of x shifted 4 units to the... Now because it's minus, because remember you're kind of like shifting over the origin, it's shifted to the right. And if you look at the graph, so the green represents the original, and the purple represents the shift. And you can see the reason I talk about the origin is for the parent functions, they go through 0, 0, unless you're talking about like the 1 over x functions, because you can't even plug in 0, so it's not going to go through 0, 0. But 0, 0 is kind of like a nice home point to be able to pinpoint your shift from. And so then if you were to sketch it, you could just do like previously whenever we were sketching the graph. You just plug in a couple points and see where it goes. Or sorry, not plug in a couple points, see where it goes, but you plug in a few points, get an idea of the shape, and then using the general shape idea, then you can get the sketch out. Now, this is what I was talking about in terms of being cautious. The fact that we talk about it as x minus h is very important because, like I said, if you see minus h, that means you're shifting to the right. If you see plus h, you're shifting to the left. So anytime you see a plus, really what's going on is it's minus a minus. But it's just easier to write plus. So just be aware that when you see that, that's implying that your h was negative because it was x minus the minus. So just be aware of that. This is just the more you know section. Now the vertical shift, this is when it's outside. And this one does go by kind of what you would think. If you add a value, that shifts it up. If you subtract a value, that shifts it down. So vertical translation is a lot easier. And so like I said, I would just make like kind of a list in your notebook or whatever you're taking notes on of just horizontal, vertical, and then when we get to the next two as well. And so these are a little bit easier because really I don't have to... Well, let me go back and kind of show one thing. So notice here, this was shifted 2 units to the left. So if we took a point like, here's the point 1, 1. If you shift it to the left 2, you now have the point negative 1, 1. So all it is just subtracting those x values and leaving the y value alone. Even 0, 0, that becomes negative 2, 0. So you kind of get the idea that these values, regardless of where they are, all I'm doing to find the shift is, if it's plus on the inside, you're just shifting all the x values to the left from the parent. If it's minus, you just shift them to the right. So, like, let's see. So here's the point 1, 1. And then I'm adding it, I'm moving it over 4. So there's the point 5, 1. So when you do the translation, you can just take points from the original and then you just do the actual translation for the graph. So then with this one, or with these two, I should say, if you know the graph of 1 over x And then you also know the graph of the cube root of x. When you did the horizontal shift, that was moving the x values. When you do the vertical shift, you're actually moving the y values. So like if we look at the first one, so the green is 1 over x. This is the function we're familiar with. Nothing too interesting about it. But again, notice the fact that every value is shifted up 3. It doesn't matter where you're at on the graph, they're always shifted up 3. The other thing this one did, and we didn't see it with the horizontal shift for the given examples, but vertical and horizontal shifts could also affect your range. Now in this case, remember, the original's range would be, so let's see, so if we have 1 over x, the range, that's going to be from negative infinity to 0, union 0 to infinity. But because we did a vertical shift up, that's now affected the range in a different way. Because notice here, we do have a point where it actually equals to 0. You can set this function equal to 0 and actually find a value for it. The problem is now, though, if I set it equal to 3, I can't find a value that's going to make it equal 3. So now the range has changed to be from negative infinity to 3. And then union, it goes from 3 to infinity. So just be aware that sometimes when you do these transformations, it will affect your domain and range. A domain example would be, let's say you did the square root of x minus 2. Like this. That's going to affect what x values you can use versus a typical square root function, which would only have from 0 to infinity. Now you could actually, you have to be careful, because notice now if you plug in 1, now you get a negative number. So if you actually lost values in this case, which is weird because 0 to infinity is infinite, but this would change the domain to be 2 to infinity, which is still infinite. Just kind of one of those interesting things about infinity. So then, like I said, with these over here, again, all you're doing, this is a vertical shift of 2 down. Notice all the values are just moved down 2. Vertical and horizontal shifts are very easy if you just take them at face value. Don't overthink it. It's just literally move every point up by a number or down by a number. Or if it's a horizontal shift, just make sure that you pay attention to, if it's x minus, it moves it to the right. If it's x plus, it moves it to the left. So you just want to be aware of those. Now the cool thing is, I say cool because I'm a giant nerd and I actually enjoy this stuff. Cool thing is you can put these together. So before we even sketch the function, let's identify, sorry I do that sometimes, I just need to make sure that what's going to pop up. Let's identify what this is. So if we drop everything that's different, so if we take out the plus 4 and we take out the plus 1, the parent function, so this is just the square root of x, and it's going to be shifted 4 units. Now it's plus, so it's 4 units to the left. And it's going to shifted 1 unit up. So a nice thing to take into account. So, and here's that transformation. And this is a really good place to talk about. So the square root of x, let's talk about its domain and its range. So we already talked about with these that there's 0 to infinity where 0 is included for both of them. You just can't take the square root of a negative number. But notice with f of x, which is the shift to the left and also the shift up, that has affected your domain and range both. So for f of x, notice the domain, the way that it's gone is I now can't get below the value of 1 because of this plus 1 here. I can make the square root of 0 by plugging in -4, but that's 0 plus 1 still. So my domain, so that was the range, so because that one was a little bit easier to talk about. So the range is now 1 to infinity. So notice 0 to infinity, 1 to infinity. We added this 1 here. But then we also back this over to the left by 4. So that means now I can include -4 and onwards to the right. So sometimes it will affect the range to where you, or the domain or range to where you gain values or you lose values. Sometimes it doesn't change it, because if you think about like x cubed, it doesn't matter if you have x plus 3, all of that. So here's x cubed versus, let's say you have x plus 1 cubed minus 3. Both of them have the same domain and range, because that domain and range were both already negative infinity to positive infinity. So if you're shifting around all the values left or right, you're still getting to use all the values. So the scary, or not the scariest, but one of the easiest mistakes is to take a specific example and generalize it to your whole understanding. And that's something that you might have, that can potentially happen here. Oh, well, I just added 1. So I add 1 to the range all the time. I moved to the left 4, so I subtracted 4 from the domain. For a square root function, yes, that's what's going to happen. For a fourth root, yes. But if you take something like a cubic function, like I said, the cubic function, you just don't have anything happen with it. So that's one thing just to be aware. Play around with them, try a few examples, and then see how the domain and range shift, or do they change at all? You want to be able to have good intuition, and good intuition means being able to extrapolate at the right times and knowing when it's a specific example at other times. Now, reflecting is kind of interesting. We talked about this one in passing before. Where I said if you throw a negative in front of a function, that reflects it over the x-axis. I may have used the word flip. Sometimes I'll be technical and sometimes I won't. So if you reflect over the x-axis, that's when you put the negative outside of the function. When you reflect about the y-axis, which would be, what's the best way to put it? Reflecting over the y-axis is when you get the same thing on the left and the right. Or that would be kind of like, instead of doing... Let me just show an example. So, x squared. You know how that function looks. So, identify which reflection it is. So with this one, it's on the outside. So this is the x-axis. This one, it's on the inside. So I'll say because it's on the outside. And then this one is your y-axis. And that's because it's on the inside. And so if you compare the graphs, so an x-axis reflection, you can see exactly what I mean. So here's this value on x squared. And so when you reflect it, it's literally just saying leave the x coordinate alone and just flip it over. So if I pick a easier point, so let me go up to the right one. So here's the point 2, 4. So think about what it says. It's an x-axis reflection. So when I come down here, when I'm at 2, I'm at -4. So all that's happened is I've left the x values alone, but I've just changed the sign of the y value. Notice I didn't say made it negative. Because if you have a negative, it becomes positive. You always be careful not to just... It's those accidental generalizations. If you're doing an x-axis reflection, then it means leave the x values alone, change the sign of the y value. So if you do a y-axis reflection, it's the opposite. Let's see, here's 4. So there's the point 4, 2. If I do, and that's on the original function. Then, if I come over here, then the point -4, I also get 2. Because what I'm doing is I'm taking the square root of the -4. Negative times a negative is a positive. So that's how we get those values. So just be careful about the reflections and what happens. Again, inside of the function, we'll flip it over the y-axis. Outside of the function, we'll flip it over the x-axis. And this was the one that we kind of briefly mentioned beforehand. So if a is greater than 1, it stretches it. If it's between 0 and 1, then it compresses it. I think I said shrinks. Shrink, compress, same thing. So then if we look at these, and sometimes you might see it written like this to kind of just make sure you're paying attention to it. This is 1/10. 0 became a 6. This is 1/10 times the square root of x. So you know, because this a is between 0 and 1, it's going to do the compression versus 5, which is going to do the stretch. So you can see here that regardless of how you stretch and shrink. I think I may have said it a bit differently that first time, but I mean, it makes sense. This one is going to be stretched a lot more because beforehand with the square root of x, when you plugged in 1, you got 1. Now you're going to have to plug in 100 before you even get just the value of 1 out, because square root of 100 will be 10. So this one has done that compression very well. And then the stretch here coming from 5, there, the 5 on the outside. Wait. So if we were to just have a comparison, let me throw, what if you had 1/2 the absolute value of x? Well, then that means at 1, you're at 1/2. At 2, you're there. See, at 4, you're at 2. So we can actually get kind of a decent idea. Oops. Let me correct that right-hand side. So let's see, those would connect. They would connect if I could actually hit the points. So this is the, oh, cool, I can't scroll backwards now. It's just going to let me write on it. All right, so vertical stretching and compressing are something that we kind of talked about beforehand. So, and the key thing is it's vertical stretching, not horizontal. So this is referring to going up and down versus left and right. I know that sounds really dumb, but it's, you have to pay attention to it, because otherwise when you just say stretch and compress, it's going to look a little off. So if it's greater than 1, this is what we talked about before. If it's greater than 1, it's going to stretch. If it's less than 1, it's between 0 and 1, that's going to compress. That makes sense. So if we look at these two functions, so if you ever see that and go, well, that doesn't quite look like the form that it should be in for a compression, that's okay. Just rewrite it in that form to get a bit more comfortable. So this one should be in compression, and this one should be a stretch. I could have looked back up. My brain stopped working for 2 seconds. And again, it's vertical compression. When I looked at it, I kind of had to take a step back, because when I think of stretching and compressing, you'll see what I mean in a second. So notice this one, everything was compressed vertically. Everything was shrunk down to a new point. Because if you think about this function is not going to have, originally if you plugged in the square root of 1, you got 1. Now it's literally going to be, I'm going to have to plug in x is 100, which is going to go way off the screen to even get to 1, because square root of 100 is 10. Then you divide it by 10, that gets you 1. So just dividing this by 10 has drastically shrunk this equation, versus multiplying it by 5. Again, this is vertical stretching and compressing. Because if you look at this, and this is what I did the first time I did it, because it's been a while since I'd taught this, I went, that looks like that was compressed. In the horizontal sense, yes, but notice vertically, everything increased. Every value went up. So it's a vertical stretch, not a horizontal one. And that's what I had to tell myself, I had to remind myself of. Versus, let's say if we did 1/2 the absolute value of x. Then at 2 we're at 1. At 4 we're at 2. At 6 we're at 3. And then absolute value, absolute value, absolute value. That is a decent straight line to have been drawn on a computer. And then I jinxed myself by saying that the first one wasn't too bad. But then notice here, these values got shrunk. Again, we're talking vertical stretch and compression. So we don't have to worry about anything in that sense. So just be aware that when it says vertical stretch and compress, that's when it's on the outside. There are horizontal compressions, but we're not going to talk about those right now. But notice the way you can get these is literally just take the original value and multiply it by whatever this stretch or compression factor is. Square root of 1, multiply it by 1/10, or divide it by 10. Square root of 2, multiply it by 10th, or 10th. Absolute value of -1, multiply it by 5. So just kind of easy things like that to identify where they need to go. Now the order of transformations, this is recommended. I won't say this is the best way, but what you want to do is always save the vertical shift for last. Because if you do the vertical shift first, it's going to be a little tricky. So this is just the recommended order. Shift it left and right, then do the compression or stretching, then do your reflection, and then do a vertical shift. So take the function here. F of x equals 2 minus x. Now, first thing to look at is, all right, what's the function we're dealing with? Now, it looks like 1 over x. So if we said the original function is 1 over x, well, it doesn't quite look like a horizontal shift. Mostly because of the fact it's 2 minus x, not x minus 2. So this is one of those weird things that takes a little bit to get used to. So 1 over x is the parent function. So we have an idea of what it's supposed to look like. I put too many eyes in this. So following our order of transformation, so like I said, I'll go back so I don't mess it up. Horizontal shift, stretch or compress, reflect, and then vertical. So, like I said, it doesn't look quite right. And the reason it doesn't look quite right is because we have it as 1 over 2 minus x. So what we're going to do here is we're going to factor out a negative from the bottom. So this is going to become negative x plus 2. Or negative x minus 2, sorry. So I'm just going to show you two kind of different ways to think about it. So negative x minus 2. And then you can factor out the negative here to put it out front. So it's negative times 1 over x minus 2. So think about what it looks like. All right, so when you do your order of transformations, so like we did beforehand, we did a vertical shift and a horizontal shift, but you can do multiple ones of those together. So key thing though is don't get ahead of yourself in some of them. This order typically works best just because of the way that everything interacts. If you choose to go any other order, it's very easy to lose certain things. So this is the recommended order, and this is what I would say to go by. Start with your left or right, then shift then do the vertical stretches or compressions, then do any reflections. This is both x and y axis, and then do your vertical shifts. That's just going to make it a lot easier. So like if you have this, let's say you had this function. So sketch the graph of 1 over 2 minus x. So first things first, what's the parent function? So the basic function or the parent function is just 1 over x. Now the problem is when you look at it, we tend to think of a vertical shift as plus or x plus or minus something, not something plus or minus x. So what we're going to do, so this is 1 over 2 minus x. I want it to look more like the x plus a number or x minus a number. So, and there's two ways to think about this. So we're going to branch off into two paths here. So first way is going to be multiply by negative 1 over negative 1. Now, if you look at that and go, okay, why am I multiplying the top and the bottom by negative 1? Because if you want it to switch into something a bit easier to deal with, you're going to have to do this vertical, or you're going to have to do this multiplication by negative 1. But the problem is you can't just multiply the bottom by it. You have to multiply the top and the bottom. So one professor I had used to always say that the hardest thing you'll ever do in mathematics is multiply by 1 and add 0. And this is one of those cases where your 1 that you have to multiply by is just a little bit kind of different. And then the adding 0, that's one of those, like, if you think about like completing the square sometimes, that would be a case of adding 0 sometime. Adding 0. Because you kind of have to change the way the problem looks without changing the values. So if I multiply the top and the bottom by negative 1 over negative 1, I get negative 1 over, and I'm going to switch the order, x minus 2. which then if I factor out the negative, now I have negative 1 over x minus 2. So now it looks like a horizontal shift of 2 to the right with a flip over the x-axis. Now the other way is factor out negative 1 from the denominator. In this case, I would say, well, this is 1 over. If I factor out negative 1 from the denominator, then I'm just changing the sign of both of these, because I'm saying I want to have a negative 1, and that means if I don't want to change the values, then I have to switch both the values. And then because it doesn't matter about the negative, I can just move it out in front of the whole thing. So then it would just turn into the above. So that's two ways to get it to look like something that you're more used to. So now we actually have exactly what we need. So this is 1 over x shifted 2 units to the right, and not flipped. Let me try and use the proper language. Flipped, reflected, doesn't matter. And reflected over the x-axis. And so if we go to the next slide, we can see those kind of the way they're done. So now the graph shows a slightly different approach. So the way I explained it was you would shift it to the right. So you would shift this one to the right too, and then you would reflect it. And so looking at the final version, we have the original 1 over x, and then we have it shifted over to the right 2, and then reflected. So notice originally it would have been kind of to think about, well, we haven't talked about asymptotes yet, so you would shift everything over 2. So this value would get shifted over 2, this value would get shifted over 2, so on. And then here, which again we said was the same as doing negative 1 over x minus 2. And and so it was shifted to the right 2 because it was x minus 2. And then it was moved, and then it was reflected over the x-axis. Now the other way you could do this one is you could technically think about it if you wrote it as 1 over negative x plus 2. You can think about this as 1 over x shifted, spelled it like it sounds, shifted right 2 units and reflected about the y-axis. Because remember, the x-axis rotation was the negative fully on the outside. The y-axis rotation was the negative only applied to the x value on the inside. So both of these are legitimate ways to get the correct answer. It's just one is a little bit different than the other. And my idea is math is getting from point A to point B as long as we all use the correct roads. And it doesn't matter if you like to take the back roads or you like to take the interstate. As long as you get to the destination and it's mathematically sound, I'm okay either way. Like with this one, you could have, this way that I wrote in the middle, this is another way that you may have looked at it originally. Is that, well, it looks like it's shifted 2 units to the right, and then it's reflected about the y-axis. Versus the way I showed was it's shifted 2 units left. Let me correct. Shifted left 2 units and reflected about the y-axis. That's just one other way to go about this one. Because the negatives, you can think about it as the negative is only applied to the x, and then it's got a plus 2, so that had to be the shifting to the left. And both ways work out. It doesn't matter if you treat it as shifted left 2 units and reflected about y, or shifted right 2 units and flipped about x. It's still going to get you the same answer. And I just want you to take the way that makes the most sense to you. If the way I did was kind of weird, but the second explanation makes more sense, go with that one. Don't feel like the way that I do it, if I approach the problem and say, this is the way I like to do it. I mean, some things like factoring, I mean, there's multiple methods, but some things there's only a few ways. So, and some things there really is only one way. But if there's multiple ways and one's more comfortable, go with the one that's more comfortable. And so the last thing for this one is symmetry. Now, y-axis symmetry, this is kind of what you can think about like parabolas. Parabolas have y-axis symmetry. So x squared, x to the fourth, x to the sixth. But notice it's basically that the negative version, or I should say the opposite sign version, is equal to the other sign. So it doesn't matter if you plug in like -1 or 1, -3 or 3, you still get the same value. Those are even functions. Origin symmetry, this one's a little weird, is that if I did f of -x, that's the same as if I did negative f of x. So like x cubed, something like that, that would be an odd function. Now, x cubed, x to the fifth, x, things like that. So origin symmetry is kind of interesting. It has that the negative on the inside is the same as if you had the other sign and the negative on the outside. So it's a little bit more confusing than an even function. So there's 3 different types of symmetry. Y-axis symmetry is you replace x with -x and you get the same thing. So that's where xy equals -xy. Or sorry. That was the even function. So f of -x is equal to f of x. X-axis symmetry is if you replace y with -y and you get the same equation. There's not really a function for this. This one is kind of you have to plug in multiple cases. And then the origin symmetry is you basically have x and y-axis symmetry. So these are special cases where these are even functions and these are odd functions. The second one is important, but mainly because we can get the odd function of both x and y-axis symmetry simultaneously, that's our preferred one. So sketch the graphs of the following relations and make use of symmetry. So first things first, 1 over x squared. So kind of some identifiers as to is it odd or even are literally look at the exponents. So this is 1 over x squared. X squared's even. What about x cubed minus x? That's x cubed minus x to the first. So the way that you go about testing these is simple. You plug in -x for x, and if the function does not change, then it's even. If you're able to if you plug in -x for everything, and in the end you're able to factor out a negative and have the original equation, that's odd. And I'll show you that one for part B. Spoiler alert. But notice with this one, so if you plug in f of -x, you get 1 over -x squared. Well, you know, if you square a negative, you're just going to get back a positive. So 1 over -x, all that squared, is just the same as 1 over x squared. Which means that f of x is equal to f of -x. And thus, we get our y-axis symmetry. And so when it comes to sketching, what it means is basically, if I plot 1, so let me just show you. So if I plot, here's 1. So the point 1, 1. So if I have 1, 1, so by symmetry, I also know that -1, 1 also is a point. Because f of x equals f of negative x. So literally you cut down half the work because you only have to find one point. So then if we go to the second one, so x cubed minus x. So I'm going to write that over here. So let's do g of negative x. Well, this will be negative x cubed minus negative x. And remember, g of x is equal to x cubed minus x. So if I do negative x times negative x, that's positive x squared, but then I multiply that by negative x again, I get negative x cubed. And then if I do negative x times positive or negative x or negative x, I get positive x. And so this is what I mean by if you factor out a negative, which was what I did beforehand. So if I factor out a negative, I just change all the signs. So this is negative x cubed minus x, which, lo and behold, negative x cubed minus x cubed minus x is g of x. So now I have that negative g of x is equal to g of negative x. So now I have origin symmetry, which means that I flip-flop the signs for these. And I know that I have the same thing. So like for here, 0, 0, can't really do much with that one. But notice here, let's take this value 2, 6. So here's 2, here's 6. And then because it's origin symmetry, that means I just change both of the signs. So, and you look over here, if I come over to negative 2, I also have negative 2, negative 6. I didn't change their order, I just changed the signs. Notice here, if I have the point 1/2 and negative 3/8, then that means by symmetry, I should also have negative 1/2 and positive 3/8. So the way I always think about it is if you're not comfortable with the idea of the whole factoring out the negative thing, check and see, did all of the signs change? When you plugged in a negative, we went from positive negative to negative positive. So all of those signs changed. That's a way to think about an odd function. When we did this one, none of the signs changed. So if you plug in negative x and none of the signs change, that's an even function. If you plug in negative x and all of the signs change, that's an odd function. So I'll end it there. This one's a little bit longer. I apologize for that. But we'll pick up next time with the next section.